Hey everybody, back in the lab again, just putting the finishing touches on this, and a little bit of celebration is in order. Welcome to the last lecture. Welcome to the end. So maybe a little celebration, a little music maybe. Maybe not the right song. Given the moment, let's try something a little different. Uh, Probably not right either. Let's try one more time and there we go. Let's just enjoy this moment. Here we are at the end. You never thought you'd make it, but we did. That's it. There's light at the end of the tunnel, kids. And here we are. All right, that's enough of that. Anyways, on with it. So today we got to talk about induction, which is going to require Faraday's law and Lenz's law. And then we got to go and we got to talk about Henry and what happens when you start inducing things. So without further ado, induction is current that is produced by a changing magnetic field. Now, before I told you that flux was going to be important to us again, and here is where flux is important to us again. So if you have flux going through a loop of a wire, so magnetic flux this time. If you have magnetic flux going through, so magnetic field penetrating through a loop of wire, what happens is you induce current if the flux is changing. So before, electric field was produced based on how much flux was going through. And now it's not going to matter to us how much flux goes through, it's going to matter how much it's changing. So is the flux increasing or is the flux decreasing? And we'll talk more about that in the next slide. So if I have a loop of wire and I bring a magnet towards it, what I'm doing is I am increasing the amount of magnetic field because the magnetic field is getting stronger. And so more and more magnetic field is going to penetrate through that loop of wire. All right. And what happens is if you use your third right-hand rule, and that's the one where you wrap your fingers around a wire and use your thumb to tell you which way the current is. So if you're increasing the amount of magnetic field going through that loop of wire, that means your fingers would wrap around the wire so that your fingers go through the loop of wire and then wrap around, because that would be the north end of the magnet would come around and connect back to the south end, right? And so you would be increasing the amount of flux going through there. And so what's going to happen is if you wrap your fingers like that, you would see that current would go up towards the top, but the picture itself has current going down towards the bottom. And the reason is that the current is going to be produced in order to counter that flux. So as you're increasing magnetic flux through the loop of wire, what happens is the wire induces a current. So what's called an induced EMF, an induced electromagnetic force, creates current in the opposite direction so that magnetic field can be produced by that current in the wire that counters it, because what it wants to do is maintain status quo. What it wants to do is keep you where you are. So you can think of what we're going to talk about with induced fields and with induced current. You can think of all of this like a spring. If you pull a spring out, it wants to pull back against you. It wants to resist that change. And so current is produced in order to create counter magnetic field. And when you add those two magnetic fields together, then they will add back up to the original because it wants to maintain the status quo. So current is created in the downward direction as it's shown in the picture here, so that you can wrap your fingers in that direction. You'll notice that magnetic field would go back through towards the hand through the loop, and that would be countering the increasing magnetic field. So current will be created to counter the increasing magnetic field. Now, as I said before, it's not the amount of magnetic field going through, it's the change in the magnetic field. So here, the hand has stopped moving, and the amount of magnetic field is going through the loop of wire is constant. Since the magnetic field is constant, then there is no induced current, there's no induced EMF because it's staying the same. Okay, now here the hand moves away, and what we're doing is we're decreasing the amount of flux. So the change in the flux, d flux dt, is decreasing now. So current is this time going to be created in the other direction in order to add more flux back through the wire, because like I said, it's not a matter of how much flux is there, but it wants to keep the same. So magnetic induction is all about keeping the amount of flux the same. And so since you're pulling the magnet away, you're weakening the amount of magnetic field going through the wire loop, which means that current will be created in order to add and try to keep it up. It should also be noted that this is only a temporary thing, so you can't keep pulling the thing away forever and keep a current. Eventually, there's so little field that it won't matter anymore, right? So this is only a temporary thing. This isn't a permanent thing. If you want it to be permanent, you have to move it back and forth constantly. If you want to see this work in action as a demonstration, you can watch either the Lewin lecture where he'll do it for you, or you can come back and you can watch any number of YouTube videos. If you just type in Faraday's law, that'll just give you a whole rundown of it. I'm sure there's a million different video things that can help you with it. So again, what Faraday discovered is that the change in the magnetic field through the loop is what really drives current or induced current. And what we find is that the EMF is equal to negative change in flux over change in time. And the reason the negative is there, this is an application of what's called Lenz's law. And it's sort of, like I said, like a spring. If you pull, it pulls back, right? And so the EMF that is created is always going to be opposite of whatever's happening, again, so it can maintain the status quo. So if you're losing magnetic flux through the loop, then current or EMF will drive in the opposite direction in order to create more flux through the loop in order to keep the amount of flux up as high as possible, as close to the original status quo as possible. And if you're increasing the amount of magnetic loop through, then an EMF will be created in the opposite direction in order to create its own magnetic flux back through the loop in the opposite direction, and through superposition cancel out other magnetic field. Again, to maintain the status quo. All right, so like we said, you have to change the amount of magnetic flux through a loop, and this can be a circular loop, square loop, whatever. But at the end of the day, you need to change the amount of magnetic field coming through, right? And so that means that you can vary the amount of magnetic field that is there with time. So instead of having a constant magnetic field, it can go stronger and weaker and stronger and weaker. Or you can change the area of the circle or loop or rectangle or whatever it is that you're coming through. Or you can change the angle that the magnetic field goes through the loop by twisting the loop in the magnetic field so that it seems like the area gets smaller. So basically you'd just be rotating that loop through. So by rotating the loop through, what you get is a change in the amount of magnetic field penetrating through the loop, because as the loop rotates towards horizontal, less and less magnetic field is penetrating through, and then as it goes to horizontal, none is, and then as it begins to rotate back towards vertical, you get more and more magnetic field increasing through this time instead of decreasing, right? And so then your current would obviously flip its direction. Now, if you're thinking, well, it's going to keep, if I keep rotating it like that, it's going to flip front, going one way, and then it's going to flip back the other way, and then it's going to go one way, and then it's going to flip back the other way. And this is the discovery of alternating current, right? And so this is how we generate a lot of our electricity, is we make something really hot, and that creates steam and pressure, or we get a lot of water behind a dam, and that creates a lot of pressure, and then we open up a tube, and that pressure will spin something that makes a very large loop of wire spin near a magnet, and we keep changing the amount of field that's going through that loop. Okay, and so if you look down here, you'll see that it is indeed it is a sine cosine function, so it's going to alternate back and forth between positive and negative current, which is how all of our stuff comes through. And then every device that we have pretty much runs off direct current, so there's a little device inside your any circuit that we have that's plugged into the wall that will flip that current from being alternating current to direct current. This is a little fun application for Faraday's here is that this is how we actually create the electric guitar, is that we have a little piece of magnetized string, and when it vibrates near the pickup, as it moves back and forth, what we're getting is a change in the flux through the pickup coil. And the pickup coil is basically a solenoid that has a wire that wraps around a cylinder a bunch of times, and then as we get more flux coming in or coming out, and it vibrates at a particular frequency, then we have a device in the amplifier that picks that up and knows what frequency that should be, knows based on the strength of the magnetized portion and the strength coming in, and that sort of amplifies the sound. And you can have different pickups to make different fatter or not as fat sounds, as they say. So this is a little application of what we called the Hall effect a couple lectures ago. And the Hall effect says that if you move a conductor in a magnetic field, all of the free charges will move to one side, and you'll create a potential difference. So all your negative charges will be on one side, all your positive charges will be on the other side, and you'll create a potential difference. And that potential difference becomes an EMF. So what we have here is called a motional EMF. If I take a bar and I move it through the magnetic field perpendicular again, what I get is all the charges will move on one side. So if you use your first right-hand rule, and you take your index finger and you point it in the direction of the velocity, and then your middle finger should be pointed down in the direction of the magnetic field, which is going into the page. You see your thumb points up, right? And so that would push positive stuff up, which means electrons or negative stuff would be pushed down, right? And so what you get out of that is all your negative charges drop to the bottom, and all your positive charges are left up at the top, and you derive a potential difference out of that. And the faster that bar moves, then the more force drives more and more and more charge to be a bigger potential difference. Now here's a little interesting fun fact. If you're pushing the bar to the right, we can do this with Hall effect, or we can do this with your motional EMF through our new Faraday's law. So if I have these two rails made of conducting material, and I have a wire connecting on one end with a resistor in it, and on the other end I just put a metal conductor on the top, and this is a frictionless surface obviously, and I start pushing it to the right, and I get velocity to the right on that bar that sits on top. Going back through the Hall effect that we just talked about, velocities to the right, and obviously I get a potential difference through the Hall effect, and we see that positive charges are driven up and negative charges are driven down. Okay, and that if we're looking at conventional current would drive current in the clockwise direction. Now, the other way that you can say this is that you can do the Faraday's law part of it, which is saying that as the bar moves to the right, then we are increasing the amount of flux that is going in through the loop. All right, and so we're adding flux down into the page, which means that current is going to be generated in the clockwise direction to counter that incoming flux. So it's going to create current in the clockwise direction that will create magnetic flux that comes out towards us in order to counter that incoming addition of flux. And that would again create a clockwise current. So either way you do it is perfectly fine. But the fun thing is, since current is created in the clockwise direction, again using our first right-hand rule, current goes up, and then magnetic field goes into the page, and so you notice that you get a resistance to moving to the right. So the bar that is moving to the right, as current picks up, begins to resist that movement. So it begins to resist being pushed to the right. And so if you start moving it fast enough and there's enough magnetic flux and you generate enough current, eventually it will generate enough to stop its acceleration. So again, the induced EMF is going through the flux, which is going to be B times the change in the area. The area is L times, or length of what we call length would be the height of between the rails, the distance between the rails, and then the change in x over time, which dx dt would just be velocity. So it's negative BLV. And again, the negative is an application of Lenz's law, just saying it's got to be the other direction to counter the change in the flux. So the induced EMF will be opposite so that it can induce a current that creates a magnetic field that will counter the incoming magnetic field or the changing magnetic field, because it wants to keep it where it was. Hey, look at that. It's Lenz's law. The induced current in a loop is in the direction that creates a magnetic field that opposes the change in the magnetic flux through the area enclosed by the loop. Boom. So for some of you that will eventually be a double E major or work with circuitry, like let's say in the computer engineering facet of things, the official formula is the closed loop integral of E dot ds is negative d flux magnetic over dt. All right, so inductance is a property that we have for what are called inductors. And that's the ability to store energy in a magnetic field and how much it can resist the change. And so we're going to talk about things like solenoids that have lots and lots and lots of loops of wire all in the same place. And we'll talk about what they do in a circuit and how they can help us. So sometimes they're there to resist change in a circuit. So if you don't want a circuit to overload and you need to smooth current out, an inductor can do that. Or if you have a couple loops of wire nearby each other and you run current through one, you can induce a current in the other, and this is called mutual induction, which means that you can run it through another. So this is an application of charging things. So like if you have an electric toothbrush that you put on a base to charge at night, what it's doing is current is running through your base, and then that also creates a magnetic field that runs through another loop. So you don't actually have to plug the toothbrush in to charge it. It just has to sit nearby and pick up that changing magnetic field that is being put out, and then it'll induce current to charge up the battery in your electric toothbrush or something else. So a couple different versions of things for inductance, and we'll talk about both. So we use EMF and current when they're caused by batteries or capacitors or something like that. And then we use induced EMF or induced current when we talk about how those things are driven by a change in the magnetic field. So self-inductance is important just to understand how circuits work and why they work the way they do. So if we have this loop circuit here, which is just a basic R circuit, just a basic resistor circuit, I've got a battery, a switch, and a resistor, and as soon as I close that switch, current begins to flow and everything begins to move as normal. But current doesn't actually come up immediately to full current or E over R. And the reason it doesn't come up immediately is because as soon as you close that switch, if you use your third right-hand rule and put your thumb along in the direction of current, you'll notice that you create a magnetic field there, and that magnetic field is going through a loop, and so then a back EMF or a back current will be created to resist that change. And it only lasts for a split second, but basically what it means is that it's going to fight the flow of current for a second before it finally seeds and everything becomes a steady state flow of current. And so what it does is it just slows it down. So current isn't instantaneously up to max, it has to build up to max over a few split seconds. So what you end up with is, through self-inductance, you end up with sort of fighting itself. Okay, and so once something gets up and running to steady state, though, just remember that because of Faraday's law, because it's up and running at a constant, there's no more change in current, so there's no more change in the magnetic field. Since there's no more change in the magnetic field, there's no more resistance to that change through self-inductance. Okay, inductance is measured in henries, and so as you go through and you see something like a 5 Henry solenoid, when they're talking about solenoids or other objects that you're going to use, what they're really talking about is an inductor or a measure of inductance. So looking over circuits, you remember going back through circuits that there was loop rule and junction rule, and so if you go through, you'll find that loop rule becomes handy again when we start talking about inductance circuits or inductor capacitor circuits or resistor inductor capacitor circuits. So that's L circuits or LC circuits or RLC circuits. So the important thing to note here is that the amount of inductance a coil can have, or how strong the inductance will be, is going to be a measure of how many loops and then the size of that area that it's going to flux through. So a solenoid is really a very simple thing. It's just a something like a hollow cylinder, right? And it just has wire that is one continuous piece of wire, and it is wrapped around that cylinder over and over and over and over. And so we have a bunch of them in our classroom that we've never gotten to that have a couple thousand loops on them. Different solenoids are used for different things. They're used in electric circuits all the time. They're used in things like your washing machine, your dryer. They've been around a long time. They're not new technology. This is fairly simple stuff. They're used in switches and in transmissions and things like that to just make sure that something happens when it reaches a certain point, or to keep something from happening too soon. So the RL circuit is a resistor inductor circuit. So that means it has a resistor in it and probably a solenoid. And what the solenoid does, the solenoid is basically going to resist change. As we said before, Faraday's law says that current and EMF are going to be induced in the opposite direction. And we said it's really important that you distinguish between induced EMF and regular EMF. And the reason it's important is when you have an RL circuit or an RLC circuit, you're looking at having both an EMF and an induced EMF. And so when you have a battery in a circuit, it drives current in one direction. But when you start adding current to a circuit, the inductor or the solenoid, its job is to resist that change, because current is going to start flowing through there. It's going to create magnetic field through its loops, and it's going to resist that change of flux. And so it's going to stop or slow down temporarily only the change to the circuit. And we'll talk about in probably the next couple slides how it's going to do that and why it would do that. Why would you want to do that? So as you have an inductor in a circuit, you close the switch, current begins to flow, and a back EMF is produced that will slow down, or as the slide says at the bottom here, make the circuit sluggish. Why would that be important? Well, for example, if you have a capacitor in the circuit, when you close a loop and you allow a capacitor to discharge, a capacitor discharges like a dam breaking. You can't control it and let it slowly come out like you would a battery. A battery puts out a certain amount of current for a long time, but a capacitor will just flood it all out immediately. And so the inductor will resist that change and sort of measure out and for a little bit slow down the current that would be coming out. All right, so we have two switches in this circuit, a battery, a resistor, and an inductor. And so what happens is, if you close switch 2, that's the one on the top, to part A, all right, then what happens is you're going to have current completely ignoring that middle wire where the B is. And then you close switch 1. Current wants to start flowing immediately, but the inductor over on the right side, the solenoid, says no, stop. And so instead of current being immediately up to E divided by R, current is going to have to slowly build up and fight the inductance that is, or the induced EMF, the back EMF that is resisting the change that is going on inside the solenoid. And so current, like I said, is trying to go through the solenoid, which would create a magnetic flux in one direction. So current, so a back EMF is being produced inside the solenoid to create a counter to that. And so it's just slowing the circuit from getting up to full speed. It's still going to get up to full speed, and it's going to do that through a time constant, much like we had with the capacitor circuits. But the interesting thing is, as it builds up and allows current to start penetrating through, and as eventually, so initially, an inductor acts like a break in a wire, but then eventually it acts just like a regular wire because there's no more change to the circuit. So if you remember capacitors initially acted like a regular wire and then eventually acted like a break in the wire once the capacitor was charged up to the same voltage as the battery. The inductor does the exact opposite. Initially, as it resists change in buildup of current in the circuit, it acts like a broken wire and doesn't allow current to flow. And then eventually, once current has built up and been steady and self-inductance has gone away, it's just another wire at this point because the amount of flux that is going through those loops of magnetic field is exactly the same all the time, and so there's no reason for it to resist any change because there is no change. The important thing that's happening there is that as it's fighting the change in the current, it's also storing up energy, much like a capacitor would. So as it allows current to start dribbling through and eventually pick up to be full E over R current, it's picking up energy and it's storing it in the magnetic field. And the reason that's important is because when you take switch 2 and you throw it down to position B, you would say to yourself, whoa, okay, well, I've taken the battery out, so all current stops. But remember, inductors aren't there just to resist current. Inductors are there to resist change in the circuit. And so what happens is, if you stop the current by throwing switch 2 to A to B, then all of a sudden the battery is taken out and current stops moving in that direction. But the inductor wants to maintain the status quo. It wants to keep doing what it's doing. And so it's going to create an EMF inside of it itself, inside the solenoid. It's going to create an EMF because all of a sudden all that flux that was there is gone. And so what happens is it starts to generate an EMF so that the flux that was there stays there. And that has an effect of continuing to drive the current in the same direction it was already going. And it's being fed by the energy that was stored inside the inductor. So I know there's a lot there to digest. You might want to play it a couple times, but just remember that when you close the switches in position A and you close switch 1, you get current that wants to run, but the inductor is going to resist that because initially it's going to act like a broken wire to resist change in adding current to the circuit. And then when you add it on, eventually it's going to come up to speed. It's going to act just like a wire. But in the meantime, going from resisting to acting just like a wire, it's built up the amount of energy inside of its magnetic field. And so when you throw switch 2 from A to B, you take away the battery, the inductor wants to maintain the flux that was there, that was created by the current E divided by R. And so it will create an EMF, E, for a little bit of time, not very long, because it can't store an infinite amount of stuff in its magnetic field, but it will store a small amount of energy in there, and then it'll use that to drive an EMF of E for a split second, and then it'll start to die out because it runs out of energy, and it will drive current in the same direction. Now, if we counter that with a capacitor that we had in the circuit a couple units ago, if you have a capacitor in there, once you throw switch 2 down to B, the capacitor is going to change directions and push current in the other direction because that was the positive end of the plate. But here the inductor is going to try to maintain everything as it was, and so it will drive current in the clockwise direction still. If this looks familiar to you, it should. This is loop rule for having a resistor and an inductor in there. And again, if you go through and you break it down and you get everything in terms of current and run everything through, you'll find that the current that an inductor will spit out is given at the bottom below just by going through and doing your loop rule, and then you're solving and isolating things and getting things to work out, and then your first order differential, and then your integrals, and then your natural log to get rid of or then your natural log, and then you're raising something to E to get rid of that. So as you go through and you do that, you're going to come out with the equation that's at the bottom here. And you'll see that this time it's negative. Before we had negative t over tau, and tau was R times C. That was the time constant. How long did it take to charge up? And we said it took a capacitor RC time. So resistor size times capacitor size. That was the time constant. Now the time constant is R over L. And so how long does it take to charge up an inductor? It takes R over L time constants, time. Sorry, I actually misspoke because I forgot that tau is always on the bottom of that. So tau is actually, or time constant is actually L over R. So if I misspoke a couple slides ago, it's just because I was looking at it as it was, but I always forgot that tau is on the bottom. So it's negative t over tau, and tau is always R times C, and so I should have realized that it is L because L is on the bottom over R, which denominator in a denominator goes to the numerator. Yay! So you close the switch, and this is how current will have to build up in a circuit with an inductor in it. It'll have to build up slowly, and then it will become asymptotic to maximum current eventually, because initially it acts like a break in the wire, and then eventually acts just like a wire. So then when you throw switch 2 down to B, and you get rid of the EMF, then it will self-induce to drive and continue current, but you see that it doesn't last that long because there's just not that much energy stored in the magnetic field, but it will fight the good fight and try to keep current moving as much as it can, but eventually will decay out and become asymptotic with zero. So when you have a capacitor inside of your circuit, it's going to store energy as electric potential energy, and that's going to be due to the potential difference across it. So it's going to store an electrical field. An inductor will store energy in the magnetic field as magnetic potential energy, and a resistor will just transform it into internal energy. So if you go back and you think about springs and those mechanical objects, right? You can think of an inductor as a spring, and it's going to store energy in that spring or in that magnetic field, and it's going to keep trying to restore the mass on a spring back to its equilibrium point, and when it goes past it again, it's going to keep trying to bring it back. The resistor you can think of as friction between the surface and the block that the spring and block system is sitting on. The resistor is going to use up energy as it goes. All right, so mutual inductance means that I have a loop of wire nearby a second loop of wire. And so that first loop of wire, I can vary the current, which would vary the amount of magnetic flux that it would create in that loop of wire. And then if the second loop of wire was nearby and geometrically positioned the right way, it would pick up that flux change, and it would begin to have a changing magnetic field through its loop, which would induce a current through that loop. All right, so that's called mutual inductance. So if you vary the currents in coil 1 here as shown, you're going to be changing the strength of the magnetic field, which will change the amount of flux going through coil 2. And based on the number of loops and the amount of area, you're going to get an induced current in loop 2. And that induced current is due to an induced EMF to resist the change in the flux. So it's not just the direction of the magnetic field, but it's whether it's increasing or decreasing in strength that is going to make the difference in loop 2. So here's where the spring block system is going to make the most sense. So I have a capacitor, which is an EMF, and then I have an inductor, which can act as a induced EMF. And what happens is if I close the switch, the capacitor is going to be free to discharge from the positive end in the in the clockwise direction. The EMF says, or the inductor says, I don't like that. And so it's going to create a back EMF to resist that, all the while storing the energy that's coming off of the capacitor. Now, eventually, the capacitor is going to run out of energy to push off. It's going to run out of potential difference. And the inductor says, no, wait, I like the game we were playing. I want that to keep going. And so what it'll do is spit out all of that energy in the form, it'll change its EMF, and it'll start spitting current out again in the clockwise direction. But now it's acting as an induced or as an induced EMF. And so it's actually driving current and energy out of its magnetic field, and it's going to charge up the bottom end of the capacitor plate as positive. Now, if we did not have the inductor in there, here's the fun part. If we did not have the inductor in there and we closed the switch, the capacitor would just discharge, and then it would start to charge up the bottom of the plate until both of them reached equilibrium. And then everything would stop. But because the inductor is there, it resists the change in the circuit as you close the switch, and so it will resist the current and the potential that is driving the capacitor. But then once the capacitor runs out of energy and potential difference, the inductor will kick in and then create its own self-inductance in the same direction this time and charge up the bottom plate. Now, once the inductor runs out of gas and has no more energy to drive an EMF onto the bottom of the bottom plate of the capacitor is then going to discharge back onto the inductor, and the inductor is going to resist that and suck the energy in as in its magnetic field. And then once the capacitor is discharged off the bottom of the plate, the inductor is going to say, nope, we're going to keep that going now. And it's going to change again and spit out current in the counterclockwise direction and charge up the top of the plate. And as long as there is no loss due to imperfect wires, so as long as there's no resistance in the wires themselves, this thing will just sit there and oscillate back and forth like simple harmonic motion. So when you're looking at this, you have a capacitor, it's completely charged up, ready to go. You haven't closed the switch yet, so all of the energy is stored up here in the capacitor. You close that switch, boom, capacitor discharges, because capacitors discharge like a dam, right? But all of that energy gets gummed up in the inductor, and the inductor is resisting stuff, but then the capacitor runs out of juice, and the inductor has all of the energy stored inside of itself. Okay, and then all of a sudden the inductor says, oops, sorry. And then all of a sudden the inductor says, well, wait a minute, we gotta keep this thing going here, and so it spits it all out onto the bottom end of the plate. And then once it's all there, the bottom end is free to discharge because the inductor was no longer able to charge against it, was no longer able to drive current onto it, no longer able to drive charge onto it. And so the bottom plate discharges, current changes direction, the inductor takes all the energy in again and says, nope, this is what I want. This is what I want to have happen. I want to resist this. And then all of a sudden, the inductor will have to change directions again because the capacitor runs out of juice. And so the capacitor will have to sit there and go back and forth, and it's going to oscillate back and forth. Okay, the RLC circuit. What fun. Okay, so the RLC circuit is basically going to act just like we talked about, right? So I have the switch in position A, and the capacitor is going to charge up. The inductor and the resistor that are in the middle branch are completely cut off. It is not a complete circuit, so no current will flow there. So all we're doing right now is charging up the capacitor. Now I throw a switch from A to B. The capacitor is going to discharge, and current is going to change directions and now run counterclockwise. It's going to hit the inductor, which the inductor is going to resist that change and allow energy to store up in there and then spit it out and start to charge the bottom. But what's interesting is because you have the resistor in there, the resistor is going to take a little bit of energy out every single time it goes around. And so it'll take a small percentage out when current is going counterclockwise. And then once the inductor runs out and the bottom plate of the capacitor is all charged up, it will spit out and current will reverse direction and begin to go in the positive direction, or clockwise, I'm sorry, clockwise direction. Thinking about rotation stuff here again, working with AP1. So then it will go in the clockwise direction, and again, a little bit of juice will be taken out, like maybe another 10%, something, who knows. The inductor will take some energy in, and then once the capacitor is completely out, the inductor will work to keep current moving in the clockwise direction, charge up the positive end. It'll sit there and oscillate back and forth, but it's going to be a damped oscillation. So it's going to be a little bit less and a little bit less and a little bit less. Look at that loop roll. And so there's your damped oscillation because you use a little bit of energy every single time in that resistor. So here's a nice little table to finish things up. Nice little way to think about things. You can compare a few things from first semester and second semester. You can sort of get some ways to think about different things. Okay. But other than that, we've reached the end. That's it. Only, what, 60 something slides? My jaw hurts. But I hope you guys are, doing well. I hope that you have enjoyed the year in terms of learning. We are not done yet. We got to do review. We got to get you ready for the AP exam. And we'll talk more about that on Thursday. But I just want to thank you guys for having a good year and for working so hard.
Dream that you dream of, dreams really do come true.